Alright, so now let's go over non-restoring division. Okay, so again, just as I did with the previous one, I'll explain what happens as we solve the problem. So let me take the same problem. I was going to take something else, but it's best to have, these two kind of side-by-side comparisons. I mean, they're not side-by-side, but who cares? Semantics, I guess. So 9 by 4. Again, let's get started, right? So Q, what is Q? Q here is going to be 9. Now 9, how do you write 9 in decimal? That's how you write it. And then D. So D here is 4. How do you write a 4? You write it like this. What about a minus 4? Because we also need a minus D, right? This is where I want you to stop and think for a second. If this is 9, can we actually take the 2's complement of this number to get the negative value? The answer is no, right? Because again, remember one very key thing. Division is unsigned. Multiplication is signed, but division is completely unsigned. Therefore, there is no notion of negative number here, but we do need the negative of D. Therefore, this is a small hack or whatever you want to call it. We add 1 MSB to the D value and make it 0, right? Because the D value was positive. So, I mean, it doesn't even matter, like it's unsigned. So we just put a 0. To get the negative D now, we take the 2's complement. So it will become 1, 1, 0, 1, 1 plus 1, which becomes 1, 1, 1, 0, 0, right? So we have all the values that we could need, right? And we are free to start our little journey. But now you'll notice some very interesting inconsistencies here, right? The size of these bits are very different. Now usually in problems you would have like 4 bits here, 4 bits here. Here you have 4 bits here, you have 5 bits here. So the accumulator's bit size depends on how many bits are in the divisor. So the divisor is made up of 5 bits, so it will have 5 zeros inside it. The Q is simply going to be copied. And you would say that since the size of Q is 4 bits, that you have to do 4 iterations. Boom, that's it. And just as we did in restoring division, you have to take a left shift to start the iteration. So let's go. Let's begin this nice little process. 0, 0, 0, 1, and then there is a blank here. Now notice, the accumulator now has 0, 0, 0, 0, 1. Now, what non-restoring division likes to do is that it likes to play life on the edge. Like it likes to play risky, right? It does not like to be stable. It like jumps around and it plays around a lot. It is very naughty. So notice what is happening here. This little value here is a 0, right? Now since this is now technically signed, D here is basically signed, you have to notice and you have to know that, this is the accumulator, right? Accumulator has to be signed here. So this 0 here represents the fact that this value is positive, right? And since non-restoring division is kind of unstable-ish and not unstable, it's just very naughty, and it likes to make a positive and a negative a positive. It will see this positive number and it will try to make it negative. How do you make this number a negative? By adding a negative quantity, which would be minus D. Minus D is a 111 0, 0, right? So you just add that, and that is basically what your new accumulator value is. Now notice something fun here. If this was restoring division would basically panic and it would go, oh my god, what is this value, take me back. But restoring is like, I do not care, I'll just be here, right? Now why did I add a 0 here at the end of the sort of Q register? Simply because we went from a positive value to a negative value. The way it works is you only put a 1 on the sort of the blank here if you go from a negative value to a 0 or a positive value, basically, right? That's how that works. And we now say that we have 3 iterations to go. That's it. Very simple. Keep moving. So let's now take the left shift for this guy as well. So we get 1, 1, 0, 1, 0. Here we have 0, 1, 0 with a blank. Look at the accumulator. We have 1, 1, 0, 1, 0. And now notice this value here, MSB, is in fact negative, right? I mean, it's not negative. It's 1, which means that this quantity is negative. And since non-restoring is kind of naughty, it will want to make this negative number a positive. Now, how do you make a negative a positive? By adding something positive, right? That's basically the idea here. So you take that 0, 0, 1, 0, 0 quantity, you try to add it. Now when you add, you'll of course notice some very interesting changes here, that it still is negative, nothing changed really. So that becomes 1, 1, 1, 1, 0 followed by a 0, 1, 0, 0, right? And now you'd say that you have 2 iterations to go. That's it, right? Now again, you would perform a left shift. Let's keep this going, right? And you would end up with 1, 1, 1, 0, 0 along with a 1, 0, 0 and a blank. Now look at the accumulator. Accumulator has 111 0, 0. Now again, the MSB is a 1, which means this is negative. Now we again, in non-restoring, we are trying to make a negative a positive, so we will add plus D, which is 0 0 1 0 0. Now notice what happens here. So 1 plus 1 is a 0, 1 carry, 1 plus 1 is a 0, 1 carry, 1 plus 1 is a 0, 1 carry. Now notice, we don't care about this extra carry bit that was generated, throw it away. Look at these 5 bits, they have become a 0, and that means that we were finally successful at least once. So 1 2 3 4 5, we put 5 zeros in the accumulator, 1 0 0 1, because we went from a negative to a positive quantity, and now we see that we have only one iteration left. That's it. You literally just have to keep this process going. It's so much simpler than Booth's algorithm or whatever, you know. So yeah, just keep going. So 0 0 0 0 1, and you end up with 0 0 0 0 1. Whoops, 0 0 1 blank. Now look at the accumulator. Accumulator is 0 0 0 0 1. Along now look at this. This value here is a 0, which means that this whole quantity is a positive. So you add a minus D to it. So again, we are trying to make it negative, you know, that whole same story again. Then nothing really changes, and you end up with this. So now you will actually have 1 1 1 0 1 along with a 0 0 0 0 1. Now notice, we went from a positive to a negative, so we just slap a 0 here. That looks like a 6 0, and now we have 0 iterations left. That's about it. Okay, so now 1 2 3 4 5, this and this is my answer. Now, as I've already sort of said in the previous division video, this is the remainder. The accumulator is now the remainder. The Q register, on the other hand, is the quotient, right? Okay, let's look at the quotient here. So the quotient simply is 2. Amazing. What about the remainder, right? Now, a very nice thing here to notice, and a very stupid trap, is you will see this 1, right? And you will notice, okay, this is negative. Can remainder be negative? No, it can't. So what should you do, right? Your restoring division instincts might kick in, and you might say, okay, let me say what has to happen here. Since we have a negative, we'll take 2's complement, bro. That's it. So you have 0 0 0 1 0 plus 1, which will end up with a 0 0 0 1 1. Boom. But notice what happens. 2 into, what was the value? I think, yeah, 4. 2 into 4 plus, what is this? This is a 3. 2 4s are 12. 12 plus 3 will give you a, what will this give? 15. Right? 15. Is this correct? We had a 9 here, but we got a 15. Oops, right? We got the whole thing wrong. Guess what? No, you didn't. Whoops, I didn't mean to create an extra page. What I meant was to grab the eraser. You know what the problem is? The problem here is actually quite simple. The problem is this step here. You're not supposed to take the 2's complement. What were you doing with the accumulator whenever you were kind of playing this game of, you know, flip-floppy nonsense? You were adding the plus or minus of D. You were not taking the 2's complement or 100's complement. You were simply taking 2's complement. So keep doing that, right? So what is this? This is a negative value. So what should we do? What was the positive D value? 0 0 1 0 0. So we will add that. That is what we will do. 0 0 1 0 0, and we get 1 0. Now 1 plus 1 is a 0. 1 carry. 1 plus 1 is a 0. 1 carry. 1 plus 1 is a 0. 1 carry. Dish the trash the extra one you get, and this is actually what your remainder is. Okay, that is the actual remainder. So your actual register configuration will become 0 0 0 0 1 and 0 0 1 0. That is the final configuration. And remember, we are not adding any extra 1 or 0 after Q, simply because we are done with the process. Note here, we wrote 0, which means we are done with the iteration. There are 0 iterations left. So we just did this little correction step for the accumulator, so that the remainder actually becomes something proper, right? Now let me do the points again. So the quotient is still 2, nothing changed. The remainder now is a 1, right? Now what was our divisor? Divisor was a 4. So 4 into 2 plus 1, what is it? So 4 2s are 8. 8 plus 1 is a 9. And guess what? The question was 9 by 4 equals what? So we have perfectly found out the answer, where 2 is the quotient and 1 is the remainder. And that's about it. The whole thing is actually quite simple and very mechanical. It's just that you have to do it a couple of times. You have to get a couple of numericals right, because in general they do not care about, if you're actually able to solve this fully or not. So, in gate and stuff like that, they'll generally be asking you the intermediate values, or just how many restoring steps had to be performed, or what the intermediate value of this particular register is, stuff like that. So yeah, that's about it. It's very simple. Sounds scary, but honestly extremely simple. That's about it. See ya.